we can proceed to next speaker, Krishna Prasad.
Good afternoon and good evening, everyone at the respective time zones. So I'm Krishna Prasad. So I'll be speaking on sloshing oscillations in hot coronal loops. We have discussed a few times this afternoon already. So before I begin, let me thank Dimitri and organizers for giving me this opportunity to share my work. So this is some work we did last year about these observations, mainly in the solar context, but I'll try to put things, describe the context in other, what we discussed like in other stellar connection, and then slowly describe the event which we studied, which is presented in this paper. So, yes. So sloshing oscillations, as we discussed a few times, are these plasma perturbations moving back and forth in the coronal loops. On the sun, of course, we are fortunate to have these resolved observations. So as you can see, there is this brightening bouncing back and forth between the legs of this loop. So these events are often occur in the flare associated coronal loops, especially you can see at one of the foot points this diffraction pattern, which is because of the bright intense flare happening in this wavelength. So so just after the flare, this perturbation originates and then bounces back and forth between the legs of the loop and before it dissipates. In the bottom, you can see the corresponding time distance map. You can see the perturbation or this moving from one end of the foot point. On y-axis, you see distance along the loop, and on x-axis, you see the time evolution. So you see this perturbation moving up and then down from one leg of the foot point to the other leg of the foot point. Correspondingly, you see this brightening moving up and down along this foot point. So these are sloshing oscillations. These are the properties of these oscillations are very similar to the standing slow waves that were observed much earlier using spectroscopic observations from Sumer. So these were interpreted in terms of slow waves, but then the only difference is that these move back and forth in space and time. So these are interpreted as reflected propagating waves or sloshing oscillations. And then there are also examples in this resolved case scenario where they show this standing pattern immediately after this perturbation. So there are standing slow waves examples as well. So I'll get back to whether they're different or what is the connection between them shortly. But before that, the slow wave interpretation of these oscillations will allow us to estimate certain parameters, for example, the plasma temperature, transport coefficients, etc. So because these are interpreted as slow waves, they propagate at sound speed, which is connected to the plasma temperature. So we can estimate the plasma temperature. The damping of these oscillations, assuming developing a theory with thermal conduction, viscosity, or different transport coefficients, we can also estimate or have an approximate values of these transport coefficients for the corresponding plasma. On the right, you see a model developed by Tongjiang Wang and co-authors. So in their model, these particular plots are from a 1D nonlinear MHD model, but they also have recently done this 3D model correspondingly, and they find similar results. So what the results mainly are that they inject a flow pulse at one end of the foot point, and then they see this bouncing back and forth motion. The difference between top model and bottom model is that in the top model, they use the classical values of thermal conduction and compressive viscosity, whereas in the bottom model, they use enhanced compressive viscosity without any thermal conduction. So as you can see that in the case of classical values, the injected flow pulse moves back and forth between the legs of the foot point, resembling this sloshing type of motion, whereas in the bottom, it immediately sets up a standing wave kind of pattern. So this kind of gives us an impression that if you see an immediate set of this standing pattern, perhaps the compressive viscosity is more, there is no thermal conduction, suppressed thermal conduction, or something like this. We can have an estimation of these or qualitative interpretation of these transport coefficients. So of course, as you have seen several times before, that these oscillations, these sloshing or slow wave oscillations have been connected with QPPs as one of the possible mechanisms of generation of these QPPs. So if we can establish this connection, then we can estimate similar parameters in stellar atmospheres to probe the stellar atmospheres like temperature, transport coefficients, or etc. So I'm showing one particular example here on the right. This has been already shown by Abhishek before. So this is a flare light curve, X-ray light curve from Proxima Centauri. So you can see the top panel showing the flare light curve, and then the sudden increase of the flux, and then you see the decaying phase. During the decaying phase, you see these up and down motions, these oscillations of the flux. So if you isolate this, the post-flare oscillatory phase, at the bottom you see that they fit two simultaneous oscillation periods. To interpret this as multiple harmonics or fundamental mode and the first harmonic, first overtone being present simultaneously in this data. So based on these observations, the period ratio between the fundamental mode and the first overtone, or the second harmonic, they could estimate the density scale height of the loops in this stellar atmosphere. So we can imagine the level of parameters which we can extract using these oscillations. So this is of course just one such example, and there are many more I'm sure you will find in the literature. For example, there is a series of works by Dimitri and recently by Krishna Prasad and Abhishek and collaborators using this thermal misbalance. You can probe even the coronal heating function. And there is also some example shown by Abhishek earlier about the loop length being estimated assuming certain temperature. There are certain approximations still. However, you can estimate the loop length of the stellar atmospheres based on these oscillations. You can estimate coronal heating function, like I told, transport coefficients, temperature, etc. Now I'm going to discuss the specific event which we studied, and then show you just to give you a gist of how actually what kind of probing we do, especially in case of resolved observations in the sun. So this is one of the observations of these sloshing oscillations in two different wavelength bands, the 131 and 94 angstroms. To give you a sense of this, the 131 angstroms looks at 10 million Kelvin plasma, the characteristic temperature of this filter, and the 94 angstrom looks at slightly cooler or 6.3 million Kelvin plasma. So as you can see this in these time distance maps on the right, you see this sloshing oscillation in both the channels, but of course the intensities are slightly different in these two channels. But if you extend this to longer time scales, in the 131 channel you don't see these sloshing oscillations anymore, but in 94 channel you see them slowly becoming this vertical standing wave kind of pattern. So this evolution of this sloshing to standing phase depends on the dissipation of the higher frequencies or the non-linear, the dissipation of the other multiple harmonics, as Valerie and Abhishek discussed a while ago. So this depends essentially on the physical conditions of the loop. So if we probe this particularly, we can talk something about the physical conditions within the loop itself. So we then estimated the parameters of this. We then estimated the parameters during these two different phases of the loop. One during the sloshing phase and one during the standing phase of the oscillations. So you can see in the bottom panel the light curves during the sloshing phase, and the top right panel the light curve during the standing phase. The clear sinusoidal pattern is present during the standing phase, whereas it's not the clear sinusoidal pattern during the sloshing phase. So we fit a particular function here for the time constraints here. I'm not describing why we fit this particular function or why at these locations. Please have a look at the paper if you want. The details are present there. But then the point is that once we fit these functions, we get the oscillation periods and damping times from these light curves here. And as you can see, during the sloshing phase, the oscillation period is about 600 seconds and the damping time is about 800 seconds. Whereas during the standing phase, which is later, you can see the oscillation period has slightly increased to 791 seconds and the damping time is all the way up to 1600 seconds. So so there is a clear difference in these oscillation properties. To understand this, we perform differential emission measure analysis, and as you can see on the panels on the right here, the top panels show the plasma temperature and the bottom panels show the emission measure. As you can see, the panels on the right here, these red diamonds show the average temperature at the loop peak, apex of the loop, as a function of time. As you can see, the temperature at the beginning is up to 11 million Kelvin or so, and then it slowly drops to 6 million Kelvin and then stays there. So the loop cools down during this evolution of the flare. And the emission measure also goes down. So there is a change of plasma temperature and emission measure over time, decrease of the values. So if you take those into account, as the plasma temperature decreases, the travel time, the propagation time of this slow wave increases along the length of the loop, assuming that loop length is constant, which is a fair assumption, I guess. And then the travel time increases, accordingly the oscillation period increases. So we estimate certain values like the oscillation period decreases by a factor of 1.28, and correspondingly the sound speed increases by a factor of 1.33 between the sloshing and the standing phase. Correspondingly, if we see the damping lengths, we can estimate the damping lengths assuming thermal conduction as the damping mechanism and taking into account especially this decrease in temperature. So we get an order of magnitude of similar values of damping lengths taking these different temperatures into account. So, so this sort of explains that this thermal conduction, we can explain the damping, and we can also explain the increase in periodicity or time. So of course, we, as I pointed before, that we have a different behavior in these two different channels. So why is this different behavior, especially in the if you see in the 131 channel, the oscillation quickly dissipates and then whereas quickly damps, whereas in the 94 channel, you see the oscillation staying for a very long time. So this has something to do with the response functions of these two channels, which are plotted in this bottom right panel. The response functions of the response function of the 131 channel, which is shown in the green solid line here, stays close to 10 million Kelvin. The peak of it stays close to 10 million Kelvin, whereas the 94 channel stays close to 6 million Kelvin, as I have shown the values before. Accordingly, the plasma temperature at the apex from the DEM measurements also moves from here to here. So initially the density is high. It's a play of the emission measure, which is higher initially. The emission measure falls, but the response function of the because of the move of this filter response function towards its apex in 94 channel, still we see these oscillations. So that's why you see the standing phase of the oscillations in this in the 94 channel, whereas not in the 131 channel. So this this shows this multi-thermal behavior of this loop. So here are my conclusions. So like I mentioned, sloshing oscillations are often observed in these flare-associated coronal loops. If we can establish the connection of these with respect to QPPs, this is still one of the valid explanations for QPPs. If we can establish this connection, we can explore a variety of plasma parameters we can probe of the stellar atmospheres using just by the observations of these QPPs. In particular, the event I have shown here, we have shown that the sloshing oscillations eventually transform into standing slow waves. I have also shown that the longer damping lengths and longer oscillation periods can be explained with respect to the thermal conduction damping mechanism. And the different behavior we see in these two different wavelength channels correspond to the multi-thermal behavior of the loop. So that's all I have to say. Thank you very much for your attention. So I'm open to questions.
Thanks a lot. Questions from audience? Any comments? So Valerina Kuryakov, please. So applause and no questions.
Can I ask?
Yes, please.
Krishna, thank you very much for your nice talk.
Yes.
So my question is that, is there any time lag seen in evolution of standing oscillations near the apex in terms of intensity fluctuations and start of motion?
Time lags between the two wavelength channels, right?
Yeah. Yeah.
Yes. So I have a slide for that. Thanks for asking. So this so these are the time lags we measured between the two channels. So between the this is 134 and 94 channel, the time lags as a function of distance. You see a particular shape. At the apex, of course, the dotted line shows the cross correlation, by the way, between the two light curves, whereas the solid line shows the time lag. The cross correlation coefficient is shown on the right. As you can see at the apex, the cross correlation is minimum, which is understandable because the signal is low at the apex. but the time lag shows a peculiar shape of like increases towards the apex and then decreases towards the foot points. So we have actually shown using a model of this, a toy model of this bouncing back and forth motions. If one of the channel propagates slowly compared to the respect to the other, then you can create this, you can get this shape of time lags. This is of course complicated because in one channel, if it is moving slowly, if it is just one ridge, you can just by the slope of the ridges, you can say, okay, there is a time lag, but then it again bounces back and this time lag increases over time, right? So it is tricky to measure these cross correlation values.
Thank you, Krishna. One small thing.
Yeah.
Is this sloshing back and forth motion is exactly the standing wave, or after some superposition, that means then this is start evolving like?
Yes, initially when the perturbation bounces back and forth, there are several harmonics of these oscillations, but then slowly the other harmonics dissipate and only the eigen frequencies or the standing wave frequencies remain. So that's what you see in the later phase. Initial phase, you have multiple harmonics present, like not just single standing wave.
Okay.
Thank you. Valery, do you have a question?
Yes, just a very quick question. Krishna, so thank you a lot. Maybe just I missed it. Have you tried to estimate the relative amplitude of the density perturbations and temperature perturbations? So just using the multi-wavelength observations.
Let me open. Yes. So I did not estimate relative amplitude of the density and temperature perturbations. We only estimated the So it seems that at the apex, the gray points here you see are from individual pixels from this region. It seems that there is multi-thermal structure here, different temperature structure here, and then it slowly cools off to the similar structure across different points at the apex. We can take these average values and then measure. Also, there are at the beginning of the time series, you can see the gaps here. During that time, because of the flare, you have the observations are the exposure times are low. You have a different type of observation, right? So because of that, you have lower exposures frequently. So because of that, we could not estimate. I did not estimate these temperatures and emission measures before. I think during this phase, maybe with a different example, which Tongjiang Wang has, they have these observations right from the beginning of the oscillation. There we can estimate, but I haven't estimated yet. We can estimate these fluctuations in temperature and density.
Yeah, because why I asked this question, because it just came to me, if you remember, so about 10 years ago was a discussion, whether the propagating slow waves are waves or flows. So I think so now this discussion ceased, we believe, so we see waves, but another argument in favor of waves would be so that in what we see, so the perturbation of the density dominates while the perturbation of the temperature, which could be seen in periodic flows, is practically absent.
Mm-hmm.
I think it's something which we possibly should think about.
Yes.
Thank you.
Sure. Thanks.
Ivan, do you have a question?
Yes. My question is like that. Krishna, how do you think? Do you have multi-temperature plasma in the same flux tube, or you have the composition of many flux tubes, like maybe located close to each other in parallel, but with different plasma temperatures, maybe some concentration as well?
Yes.
How do you think?
Yes. So if you consider by same flux tube, if there is a possibility of interaction of the plasma, you cannot have multi-thermal temperature because of the thermal conduction. So if we consider flux tube as an individual strand, I would say that this loop is composed of multiple strands, which can have different temperature plasmas isolated from each other.
Sorry for the contribution to the discussion. Ivan, do you mean so the same volume has several different temperatures? I think it's impossible, just so it should be a single temperature.
Yes, this is what I mean.
Yes, if it is a single flux tube or a single tube within which the plasma can interact, then I don't think there will be multiple temperatures. But then
temperature, yes, it should be a single temperature. So temperature is just the width of the distribution function.
Yes.
Now it depends on how your how to say, like equilibrium will be achieved by which time? I mean, because you need
Well,
enough of collisions of plasma to be
Yes.
like.
Yes, but in the considering these hot temperatures, the thermal conduction is very high, and it quickly balances out if the plasma can interact. But if you isolate them in different flux tubes, different strands of the tube of this, even within the same loop, then you can have multi-thermal structure. That's what is happening here, in my opinion.
Yeah, and in this case, you need some kind of coherence of like waves, or like in such kind of multi-threaded
Yes.
structure. Yeah.
Yes. So I think that coherence is already brought by the heating function. So you have a loop even without oscillation. So if you consider this loop as bundle of strands already existing, then this oscillation is just a manifestation on top of that loop. So that coherence is brought by the heating function, not by the oscillation itself, in my opinion.
Yeah. Okay. Thank you.
So thanks again for your talk and discussion.